Isaac Newton described his laws of motion and gravitational theory in his book, The Principia, which was published at the urging and actually at the expense of his friend, Edmund Halley. Halley was later made Astronomer Royal, and in those days, the Astronomer Royal was also director of the old Greenwich Observatory. Now, according to Newtonian theory, all objects attract all other objects, but small objects like these attract themselves exceedingly weakly. It's very difficult to measure the force between them, and consequently very difficult to calibrate the strength of this gravitational pull. To be sure, it's easy enough to measure the force with which the Earth pulls on something, because that's the object's weight. But unfortunately, we don't in advance know the Earth's mass. And if we don't know the mass of the Earth, we can't tell how much a given amount of material will pull on something. So it works out that the actual calibration of the strength of the gravitational force, the so-called constant of gravitation, and the mass of the Earth are really the same problem. Find one and we find the other. But that problem was not solved for nearly a century after Newton introduced gravitational theory. The first person who did solve the problem was another Astronomer Royal, Maskelyne. His method was crude, but it was deucedly clever.
Newton produced laws of motion and a law of gravitation. And the value of the constant of gravitation, which tells just how strongly two masses are attracted together, was first measured here near the mountain Schiehallion in Scotland. The measurement was made by Neville Maskelyne in 1774. He'd just been made Astronomer Royal at the time. And he chose this mountain because it's so beautifully symmetrical that he could calculate the mass of it. And the other mass he used was a plumb bob. His method was really very direct. What he did was to suspend a plumb line on one side of the mountain, close enough to the mountain that the bob was pulled a little to one side by the attraction of the mountain. And he recorded that position by measuring the position, the angle of a star with respect to this line. Then he took his apparatus over to the other side of the mountain, suspended the line again. But of course, this time the plumb bob was attracted the other way to the mountain. So the position of the star with respect to this line moved a little bit. And then by taking this shift of the star and the calculated mass of the mountain, and of course the mass of his plumb bob, he was able to calculate the value of the constant of gravitation. And I think this measurement shows the grandeur of Newton's laws, because this constant measured here on Earth operates over the whole solar system. And in fact, the success of Newton's laws over the solar system was clinched by the discovery of Neptune, because the position, indeed the very existence of the planet Neptune, was predicted using his laws.
These successful Newtonian laws depend only upon acceleration, not upon velocity. By this I mean that when you combine a law of force with the laws of motion, you get an expression for the acceleration, an expression which gives you the acceleration at each point. So the laws of force depend only upon the acceleration. Consider, for example, this bucket of water here. When the water is stationary, the surface of the water is flat, as you would expect. Now, let's rotate the water. Of course, to speed up the water like that, we need a force. In this particular case, we have a magical force. You will notice that as the water speeds up, the surface of the water is no longer horizontal. It departs from the horizontal in a parabolic shape. Now, that surface of water gives me the shape of the force law in my coordinate system. Is there another coordinate system which will have the same force laws and therefore have the same shape of the surface of the water?
I have a rotating bucket, much like the one which Al had on the shore, but I'm moving uniformly relative to him. But the water surface in the bucket is behaving just in the way it did on the shore. It's curved and it's symmetrical. It's not distorted in any way by the uniform relative motion. So here's one experiment, at least, which is not affected by uniform relative movement between observers. I can do other experiments as well. For instance, if I toss a coin, it falls back in my hand in the same way as it would on the bank. And I get the same number of heads and tails as well. In fact, we believe that all experiments give the same results for uniformly moving observers. So just by looking at these experiments, there's no way of telling whether it's Owl that's moving or me. This sort of relativity, the laws are the same for observers in uniform relative motion, is called Galilean relativity. But it only applies to uniform motion. Accelerated observers should not see the same laws.
I am rotating with the water, so the water is stationary in my coordinate system. But I can tell I am rotating because the water is curved. And besides, I'm dizzy.
I'm also at rest with respect to the water, but I know that I'm not rotating because the water surface is flat. So accelerated frames can be distinguished from each other, but uniformly moving frames cannot. That is a statement of Galilean relativity. And in fact, everything we've talked about up till now can be summarized by saying that Galilean relativity is consistent with Newtonian mechanics. And in Newtonian mechanics, forces depend only on acceleration. There can be no special velocity, and all velocities are possible, no matter how great. All speeds are possible in the Galilean scheme because speeds simply add up. If I have two boats approaching me from opposite directions, one maybe at 5 knots and the other perhaps at 10 knots, then the way the scheme tells me how to work out how fast this one will see the other one approaching is simply to add the two and get 15 knots. And if speeds do add in that way, then I can get speeds as high as I like. But the deepest and most enduring idea which Galileo had was the one which I mentioned on the lake, that laws are not changed by uniform motion, the principle of relativity. And we'll be coming back to that again and again. The way Galileo himself put it when he described the principle for the first time was like this. He said, imagine yourself below decks, shut away in a cabin on a large ship, and have with you a bowl of water with some fish in it. The fish will swim around indifferently in all directions, and if the ship is moving uniformly, you won't be able to tell by looking at the fish or by any other means how fast the ship is moving. Or indeed, whether it's moving at all. One way we can put the relativity idea to work on a far grander scale is on a problem which came up during Newton's lifetime and which was very important to him, the question of whether or not the speed of light is infinite. We can use the principle of relativity to interpret observations of the natural satellites in the solar system.
The planet Jupiter has at least 13 satellites, but the first 4 were discovered by Galileo. A convenient way to time how long it takes a satellite to revolve about Jupiter is to time the interval between successive eclipses of one of the satellites into the shadow of the planet. Now, the Danish astronomer Olaus Rømer was trying to do just this experiment in 1675, but he discovered a rather remarkable thing. It seemed as though the period of the satellites of Jupiter were longer when the Earth was moving away from the planet than some months later when the Earth was moving toward Jupiter. Now, the law of gravitation says that the period of the satellite should depend on how far it is from Jupiter and on the masses of the objects, but it certainly should not depend on the motion of the Earth, any more than Alan's flipping of the coin should depend on whether the boat is moving toward or away from shore, or how the fish swim in the tank should depend on whether the ship is at sea or at anchor. See, that would violate the Galilean principle of relativity. Well, Romer instead, correctly, realized that light must travel at a finite speed. It works this way. Suppose we start timing when the satellite dips into the shadow of Jupiter, while the Earth is moving away from Jupiter. Now, to bring us news of the next eclipse, light will have farther to travel because the Earth is moving away, so it will seem to take longer between the eclipses than it would, say, 6 months later, when the Earth is on the other side of its orbit approaching Jupiter. Now it moves forward to meet the oncoming light, bringing us the news ahead of time. Well, observations of this sort show that it takes light about 16 minutes to cross the orbit of the Earth. And that means it takes, that light travels at a speed about 10,000 times the speed of the Earth. But we can also measure the speed of light by timing its passage over very accurately measured distances right on the Earth. Galileo himself suggested how such an experiment could be done, but he realized that light travels too fast to measure its motion by so crude a technique as he had proposed. However, in the 19th century, the physicists Fizeau and later Jean Foucault both made very delicate apparatus with which they were able to measure the speed of light to within just a few percent. But by far the most famous such experiment was done in 1926 by the first American scientist to win the Nobel Prize, Albert A. Michelson. Velocity is how far something moves in a given time. So to measure the speed of light, Michelson had to have not only a very accurate timing mechanism, but he also had to have a very accurately measured distance.
Good afternoon, sir. No worries. Here we are.
Moreover, Michelson wanted his light path to be at as high an elevation as possible to avoid haze and smoke and heat currents that might occur near the ground. He selected 2 peaks in the San Gabriel Range in Southern California. One was Mount Wilson, famous for the observatory, and the other, Mount San Antonio, or sometimes called Mount Baldy, 22 miles away. Michelson needed to know the distance between those 2 mountain peaks to a precision of only 7 inches, and yet the terrain between the mountains was extremely rugged. He asked for and received the help of the U.S. Coast and Geodetic Survey. Also, being a Navy man himself, he got help from the United States Navy as well. The teams began the surveying in 1922 and completed in 1923.
Thank you very much. No problem.
In Michelson's apparatus, located on Mount Wilson, light from an arc lamp was bounced off a rotating 8-sided mirror, and then by a series of reflections to San Antonio, 22 miles away. There, a second series of mirrors sent the beam back to Mount Wilson, where it was redirected onto the 8-sided mirror, but now to the side symmetrically opposite that of the first reflection. But during the light's round trip, the rotating mirror had turned slightly. Thus, the final reflected beam would pass into the viewing telescope and be observed, only if the mirror made exactly 1/8 turn, bringing the next facet into alignment. Well, Michelson had only to measure how long it took the mirror to make that 1/8 turn to time light on its 44-mile round-trip journey. The heart of Michelson's apparatus was the 8-sided mirror, and it was a testimony to his ingenuity as an experimenter. Michelson set the mirror rotating by means of jets of compressed air. He could make it spin at any rate up to nearly 600 times a second. The light beam itself, passing from Mount Wilson to Mount San Antonio and back, was in places intense enough to start a forest fire. In actually taking the observations, Michelson would adjust the speed of the rotating mirror until the final reflecting beam was reflected into his telescope where he could observe it. Then the actual speed observed for the rotation of the mirror told precisely how long it took to make that 8th turn, which is how long light took to make that 44-mile round trip to San Antonio and back. The experiment gave a pretty accurate value for the speed of light in air. But light is slowed down in moving through a transparent medium. And even in air, its speed is reduced by about 70 kilometers per second. Modern measurements of the speed of light in a vacuum give the value 299,792.458 kilometers per second. This fundamental physical constant is now universally denoted by the lowercase letter c. Michelson himself designed an experiment to measure c, the speed of light in a vacuum. He built a mile-long vacuum tube at the Irvine Ranch near Santa Ana in Southern California. Unfortunately, Michelson died before the experiment could be complete. The remains of his vacuum chamber, now derelict here on Mount Wilson, are these tubes.
Michelson sent light down a vacuum tube. Today we can send matter down a vacuum tube and accelerate it with electrical forces. A few hundred miles north of Mount Wilson in Northern California is the Stanford Linear Accelerator Center, SLAC, a 2-mile-long vacuum chamber designed to test the behavior of particles of matter under extreme conditions, an attempt to understand how nature works at its most fundamental level. At SLAC, the lightest of the elementary particles, electrons, are accelerated to extremely high speeds.
The source of the electrons, where they start their journey, is here. It's a very simple source. Behind all this is just a red-hot wire, like you'd find in the back of any TV tube. The hot wire liberates electrons, and as soon as they're free of the wire, they're accelerated by a voltage of 70,000 volts, 4 or 5 times higher than you'd find in a TV tube. Now, in the first millimeters of that journey, we can be confident that the electrons are following Newton's laws of motion, because their speed over that small part is lower than the speed of the Earth and the planets in the solar system. And Newton's laws have been checked very well for those speeds. But the mass of the electron is so small that by the time the electron passes the 70,000 volt electrode, it's traveling at half the speed of light. And that means that this apparatus gives the possibility of testing Newton's laws far more severely than can be done by any observations in the solar system. So let's follow the electrons. They come along here, and they're twisted right around by a magnet and aimed down the tube. And then, as they come along, these coils hold them in course and keep them bunched into a narrow beam. Now, if Newton's laws of motion are right, this second shot of acceleration should raise the speed of the electrons from half that of light up to the full speed of light. And then, as they travel along here, accelerated all the time, by the time they come to the end of this section, according to Newton, they should be traveling at 5 times the speed of light. But that's not what happens. In fact, at this point, the speed of the electrons is still below the speed of light. It's about 1/3% short of it. So already, at this point, a clear departure from Newton's laws of motion. But this is just the start of the tube.
Along the whole length of the tube, the stage of acceleration is repeated over and over again. so that by the end, the Newtonian scheme would expect the electrons to have overtaken light by an enormous factor, 300. That 1/3% gap between the electron speed and the speed of light is gradually reduced, but never closed. This has been checked very precisely at SLAC by having light and electrons race each other down the tube. They arrive at the far end practically together. These are the fastest electrons man has produced, but they never overtake the light beam. So, at very high speeds, applying a force increases the energy of a particle, but hardly increases the speed at all.
Under these extreme conditions, Newton's laws totally break down and new laws are needed. They must be very similar to Newton's laws at low speeds, where, after all, his laws work very well. But at high speeds, they must be very different. And it's Galilean relativity which provides the clue for how to look for these new laws. It's the man on the shore and the man on the boat all over again. Think of me as the man on the shore this time, and the electron travelling along the tube is the boat. And these new laws, whatever they are, must be the same for me and for the man travelling with the electron. And these new laws, whatever they are, must explain this striking fact that the boat, whatever its power, cannot travel faster than the speed of light. Nothing can be pushed past that limit. In the hands of Einstein, these two clues were enough. He produced a new framework of dynamics based simply on the idea of relativity and of the special importance of the speed of light as a limiting speed. Einstein's new framework brought with it changes in the ideas of space and time, changes which seemed subtle at first, but at high speed, the effects are enormous.
What we can test today, Einstein did in his imagination at the beginning of this century. Einstein acknowledged Newton's achievement. Newton, forgive me. You found the only way which in your age was just about possible for a man of highest thought and creative power. The concepts which you created are even today still guiding our thinking in physics, although we now know that they will have to be replaced by others farther removed from the sphere of immediate experience, if we aim at a profounder understanding of relationships.
Physicists had to accept those new ideas in order to build this machine and so produce beams of electrons with vast energies. When those electrons collide with matter, they penetrate so deeply as to reveal the innermost structure of the matter. And in those collisions, there are sometimes produced new particles, particles which are filling out a pattern, a mosaic, of which before we'd just seen one small corner. We don't know yet how far that mosaic extends.